So in the last lecture, we talked about most of the important thermodynamic quantities that are of interest for an ideal gas, but we didn't talk about the chemical potential. We stopped earlier than that. And though in many contexts people tend to kind of ignore the chemical potential, they use Gibbs free energy instead, or they use something they call Gibbs free energy instead, it's really the most important quantity for chemists. So I've reserved an entire section of these lectures basically to devote to the chemical potential, and then also to an example that we'll do at the end where we calculate all the quantities we can now calculate from StatMech. So over on the left-hand side here is all the complicated formulas that you get when you plug our basic expressions from StatMech first into the Helmholtz free energy, and then we take a derivative with respect to n in order to get the chemical potential. And that gives you this rather complicated expression, especially since each of these partition functions are also complicated, so really a pretty complicated thing. And we could plug straight into that, and in a lot of cases that's what the textbook does and so on. But I've tried to simplify things. So over here on the right-hand side, I've got a formula that looks a lot simpler and is easier to interpret. And that's what I'm going to actually talk about. I'm going to talk about what's in this formula on the right-hand side and hopefully get everybody to the point where it's not too bad to actually do calculations using that formula. So I'm going to skip, or coming back to the left over here, I'm going to skip all this stuff. That's derivation. And I encourage people to look at that, but you can see there's a fair amount of it, and what it's all getting to is this expression down here, which is exactly the same as the expression on the right. And so let's just look at that expression and interpret it, because it will be important, especially when we talk about chemical reactions later. So first of all, what this expression is saying is that the chemical potential is RT times the logarithm of, that's the usual activity. So that's the concentration, that's the usual activity that we've been dealing with since early on in the thermodynamics section, divided by something called A mu 0. And here's what A mu 0 is. It's a whole bunch of partition functions all clustered together. And I've given it a name here. I've called it the activity of microstates. And what that says is that this quantity up here inside the logarithm is the ratio of the activity due to concentration of gas molecules over the activity of the actual microstates inside those gas molecules. And this quantity A mu can also be interpreted, and both interpretations are useful, as the number of microstates available to one molecule when it's at standard state concentrations. So it's a sort of standard state activity, if you like, for microstates themselves. Notice that it involves all the partition functions, and the partition functions count microstates. And so when I say the activity of microstates, it's essentially the concentration of microstates that's inside all the molecules that make up your ideal gas. All right. We're going to calculate this quantity A mu 0 down below later. But for the moment, let me just look at all the things that go into it. First of all, notice that there's a C0 here. That's the actual standard state molar concentration. Usually, that's just 1 molar, but I've put it in as a variable, so if the standard state concentration isn't 1 molar, you can plug whatever the actual standard state concentration is in molar units. Then there's this quantity that appears in the denominator of our activity up here, our microstate activity here, and that can be interpreted as the partition function, the translational partition function at standard state conditions. And we saw earlier when we were plugging in all the fundamental constants and all the units conversion factors and stuff, that quantity can be simplified. And if you want to if you're not interested in knowing what all the fundamental constants are that go into it, all you got to do is know this number, 0.46009, times the actual molecular weight in grams per mole, so no units conversions necessary, times the temperature in degrees Kelvin. You plug those numbers in straight, take the 3/2 power, and you can calculate this, this translational partition function. Then there's the vibrational partition function, and I put a bar over the top of it to indicate that I've left out all the ZPE factors. So all the 0-point energy factors are gone from up here. We've kept them. They're over here. They're actually still present. They're in this ZPE term that's tacked onto the end of the chemical potential, but I've taken them out of the vibrational partition functions, so these are just the parts of the vibrational partition functions that count microstates. And that's all that's in there. And then let me get rid of some of this junk. Then the last factor that's up here in A mu is the electronic partition function, again with no ZPE factor. Again, I put the ZPE factor over into this term over here. It's all those ZPE factors are buried into one giant ZPE factor inside the chemical potential. And normally, of course, this second term in the sum, the term that comes from the first excited electronic state, also is essentially zero. And so everything just reduces to just the ground state degeneracy, which is usually 1. There are lots of molecules around where the ground state degeneracy isn't 1. For oxygen, O2, for example, it's 3. But in most cases, anyway, it's just 1. And so usually, the most common case, anyway, is that the ground state partition function, the electronic partition function is just a 1. All right. So that's defining all of our quantities that go into this expression for the chemical potential. But it would be good to actually get some practice calculating all those quantities, and so let's do an example. All this stuff is just the stuff I just said before. And we're going to do that down here. Here's the example. We're going to calculate everything. We're going to calculate all the thermodynamic quantities. But before we do that, let me just point out that once we have the chemical potential, once we have this formula, this statistical formula, we're pretty much able to calculate every quantity. So one of the quantities we can calculate is the entropy. And I've plugged some formulas in down here, but really we can use this formula up here directly and straight. We have now formulas for the thermodynamic internal energy. It's an ideal gas, so this PV over T is just an NR quantity. We have that. Now we have an expression for the chemical potential. We have N and temperature. So we can just use this Euler relationship for entropy and get the entropy out directly. And now we can do that with everything. This is just the Euler relationship for Helmholtz free energy, the Euler relationship for Gibbs free energy, the Euler relationship for enthalpy. We now have all the quantities we need for these things. We have PV and mu n. We have, it's just mu n for the Gibbs free energy. We have the thermodynamic free energy, the thermodynamic energy, or the mean energy, if you like, and we have nRT. So we can calculate everything now, and let's do an example where we actually do all that. Let's see how that actually looks in a concrete example where we plug numbers into everything. I have chosen an example. I've chosen I2 to do our example. So we're going to calculate all these quantities. We're going to calculate everything we can think of for this one molecule I2. So we're going to calculate the internal energy, the two heat capacities, the chemical potential, the entropy, the Helmholtz free energy, the Gibbs free energy, and the enthalpy, all those things for I2 over here. And I chose I2 because it's such a heavy, soft molecule that the vibrations will contribute. Most of the molecules you'd pick, like oxygen or nitrogen or other molecules in that chart we looked at earlier, the vibrations really don't contribute anything, but for I2 they do. We've seen that above already in the value for the heat capacity. And so I chose this so we get some reasonable contributions for vibrations, so we get some practice calculating vibrational contributions. Also, I chose the conditions under which we're doing these calculations to be standard state conditions, or very close to standard state conditions anyway. Pressure of 1 bar, 1 mole of I2, and temperature of 300 Kelvin. I chose 300 rather than 298 because 300 is easier to plug in, but very close to 298, so almost exactly the table conditions, not just the standard state conditions, but the actual table conditions. So we compare the answers we get to answers in the table. So that will be, how good do we do? That's an interesting question. We'll be able to answer that question doing this calculation. All right, I'm going to push this off to the side a little bit now. In fact, I'm going to push it all the way off so we can get a better picture of how we're going to proceed. Well, we're going to calculate everything, and so the very first thing I did anyway was just gather together all the formulas. I'm not plugging any numbers into these formulas yet. I'm just gathering together all the formulas I'm going to need for all these quantities and get them all straight, all on one page. So there's the energy, and of course it's got all the little pieces that go into it, the translational, vibrational, rotational contributions. I've set the 0 point energy to 0 here. There is a 0 point energy contribution, of course, to the total energy. The 0 point energy adds to the total energy. I've set it to 0 here because we're only dealing with one molecule. It's just I2. Later, as I keep saying, we're going to have to keep those ZPE terms in order to account for differences between molecules in chemical reactions. But for the moment, we're not there yet, so I set it to 0. Here's the heat capacity contributions. We already looked at all those things. This is a linear molecule, I2, so these nonlinear contributions don't count, and the ones we want are the linear contributions, so we've got everything there. Cp is just Cv plus Nr. Here's the formula we just looked at for chemical potential. We're going to get a chance to use that now. Remember that these activities, and especially the microstate activities, involve all the partition functions for our molecular partition functions for our I2 molecules. So we're going to need all these formulas too, but here they all are. And then we can calculate entropy, A, G, H, just using the Euler relationships that we got from StatMech. Because we have all the quantities now that we need to plug into those Euler relationships. All right. We have pressure of 1 bar, 1 mole of stuff, temperature of 300 K. That's some of the stuff we're going to need. Now I'm gathering all the data that I need. So here's the numbers I'm going to need, the conditions I'm going to need. And then I'm going to need some molecular properties I'm going to need for the vibrations. I'm going to need the vibrational temperature. For the rotations, I'm going to need the rotational temperature. I'm going to need the molecular weight for, basically for the translational partition function. That's 254 grams per mole for I2. And we've seen those values in tables in lecture notes 8 earlier, and they're in the book, and you can find them on the internet. If it comes to finding these kinds of values, vibrational frequencies, vibrational temperatures, rotational moments of inertia or rotational temperatures, then those quantities are common on the internet. And if I ever don't give them to you, like in a problem or the practice exam, for example, I may not actually, now that I think about it, I may not give them to you on the practice exam, so you get some practice finding them on the internet. They're easy to find. And they're common. For these small molecules, anyway, they are. For less common molecules, they're hard to find. But for these small, easy molecules, they're easy to find. All right, now we just have to start plugging in to the formulas we already have. Eventually, we're going to need the activity. We're going to need it for the chemical potential. And we're going to need all these partition functions for the activity of microstates that also goes into the chemical potential. So now I'm just plugging in for the activity. This is N over V, this P over RT stuff here, is just the molar concentration of I2. I chose 1 bar, so I didn't choose a molar concentration, I chose a pressure, but I have the ideal gas law, so I can get what my molar concentration is. It's P over RT. I plug those numbers in and I get an activity or a molar concentration. It's really unitless, right, because I'm dividing by my standard state concentration here, which is 1 molar. But effectively, it's 0.04 molar concentration. Then for QR, it's for a linear molecule, a sigma factor of 2, rotational temperature I have up above. Plugging in, I get about 3,000 microstates for the rotational partition function. For the vibrational partition function, again remembering without the ZPE factor, I just have to plug in the value of the vibrational temperature up here. Again, remember, we've seen this before for I2, but its vibrational temperature is exceptionally low because the bond is weak and the atoms are heavy. And so I plug that value in here, 308, and I get a value of about 1.6 for 1.6 microstates for the vibrational partition function. That's large for a vibrational partition function, right? This is an exceptionally low vibrational temperature. And so even though that's not a very big number, it's big for a vibrational partition function. The ground state of I2 is not degenerate. There's only one unique ground state, so the partition function, the electronic partition function is just 1. And finally, this standard state translational partition function, which is all this stuff in the denominator for our formula for the activity of microstates here, that we can get by just plugging into this nice convenient formula I did. So that's molecular weight, that's temperature, and it gives us about 6 million microstates, translational microstates at standard conditions. Finally, we plug all those quantities in, all the partition functions up above, and this guy that we just calculated. That's all these numbers multiplied together, and that gives us about 3 times 10 to the 10th microstates in our microstate activity at standard conditions. Notice that there's 2 main places where these microstates come from. One is the big one is the translational contribution, and the next biggest one is the rotational contribution. Both of those, well, this one especially, but both of them really, are larger than what you'll get for most other molecules. I2 is especially heavy and especially soft, and so this is a bigger number than you'll get for most molecules, but it's not hugely bigger. You'll get something 10 to the 8th, maybe, I think, for most molecules. All right, now we're going to need, eventually, the energy. In fact, the energy is one of the things we want to calculate. Here's all we have for this case. This 5 halves is the rotations and the translations combined. Here's the vibrational contribution. So if I plug in for N and R and T, for N is 1, right, T is 300. For the rotations and translations, we get about 6 kilojoules per mole. The vibrations in this case contribute something significant. I calculated that number separately and left it separated out like that so we could see how big the vibrational contribution was. And it's about 1,400 joules, which is still considerably smaller than the rotation translation contribution, but significant. And so the overall number is about 7.5, almost 8 kilojoules per mole. Now we can calculate the heat capacity, the CV value. Again, there's the rotation translation contribution. That turns out to be 20.8. That's what we've seen before. And the vibration contribution in this case, again, plugging the vibrational temperature into our formula, gives a considerable contribution from vibrations again because I2 is so soft and so large. So about 8, a number of about 8 joules per K for the vibrations in this case, for a total value of 28.4 joules per K for CV. Cp is a number that we can actually compare to values from the tables. And we get it just by adding NR, which in this, N is 1, right? So it's just 8.314. That gives a value of 36.72. The value in the tables is 36.9. So we get very good agreement. After all this work, after all this stuff that we've done, all these little contributions that we've added up, it's surprising that there isn't more error somewhere along the line, right? When you're making all these calculations, you got to think, somewhere along the line, something's going to be wrong. But in fact, the agreement is remarkably good, 36.72 versus 36.9. I don't know what the extra little 0.2 difference is due to. Might be electronic contributions, I don't know. Or it might just be experimental error, for that matter. Now the chemical potential. That's the big one that we just learned how to calculate up above. But we've already got the little pieces that we need, right? We've got the activity, that's 0.04. We've got the activity of microstates, that's 3 times 10 to the 10th. RT is easy, and we've set this 0 point energy to 0, so it's an easy calculation at this point, and we get minus 68 kilojoules per mole for the chemical potential. We're going to use that now over and over in calculating all these other things. First, the entropy. That's the energy that we just calculated above divided by T, so there's our about 8 kilojoules per mole divided by 300. That's the PV over T term that normally appears in the Euler relationship. We use the ideal gas law to turn that into an NR. That's just an 8.314 now. We just calculated the chemical potential up above, 68 kilojoules per mole. Divide it by temperature here, and the net result is 260.68 joules per K. Notice this is not a delta S. This is an absolute third law entropy. And we've just calculated it using the Euler relationship. That's also the value that appears in the tables. It should agree. And in fact, it does agree. In fact, it agrees so well that I have to believe that we're getting lucky by accident here, because nothing ever agrees as exactly as this is agreeing. So, there's another point to make about that agreement. We used this energy value, we used this chemical potential value in order to get this value for entropy that agrees so well. It wouldn't agree if these energy and chemical potential values weren't also good. So that suggests, I mean, it's not a rigorous proof, but it's very suggestive that all the other values, the energies, the heat capacities, the chemical potentials, all the other values we've been calculating all along, they probably all agree. And if we get agreement with entropy here, which depends on all those things, probably those other things are good too. I mean, it could be that this is wrong and somehow by luck they cancel, and we get the right answer out anyway, and that does happen from time to time. But probably they're pretty good. They're probably not very far off either. And now we can do the rest of it with the rest of the quantities. We can do Helmholtz free energy. That's just minus nRT plus mu n. That's again the Euler relationship. Plugging the numbers in, we get minus 70 kilojoules. Gibbs free energy is essentially the same thing, and exactly the same thing, in fact, in this case, because n is 1, as the chemical potential, so minus 68. And finally, the Helmholtz free energy is just our energy plus an extra nRT, and that's about 10 kilojoules per mole. All right. That, I think, is everything I wanted to say when we're calculating just the properties of one molecule at a time, or one type of gas. The next thing we're going to do is talk about chemical reactions where we're going to have a whole bunch of different kinds of molecules all as part of the same system. But that's a fairly complicated topic, so we'll take that up next time.